All right, folks, can you hear me? Yes, I see some thumbs up. Awesome. All right, so we're going to try something new and different. So I am on travel. I'm in a hotel room right now, but we're going to try to teach in class. Gokul, can you mute yourself? Because I'm hearing feedback and it's really weird.
Okay.
Or maybe I can do that? Oh, cool. I can mute you and unmute you. Okay.
Okay.
So then what I'm gonna need you to do is to like wave. I don't know. The people in the front row, I can see you very well. So I don't know, wave or do something if yeah, exactly. And I'll unmute you so I can answer your question. Are we good?
Yes.
Cool. How's the assignment going?
Good.
Yeah. Do you see everything coming together? All of the bandit levels, all the exploitation stuff we've been learning are all coalescing in this one assignment. So this is really the kind of crux of the class. And if it wasn't brought up already, this will be basically the final assignment. So there's this assignment, a final, and we're done. Don't all start clapping at once. Yeah. All right, awesome. Cool. Well, let's get started. So hopefully you all viewed the lecture that was posted yesterday. So we're going to kind of go right from there. So basically, to catch everyone up, if you didn't view that lecture, you should definitely go back and see that. The goal here is to, that class was talking about x86 assembly code, so trying to look at how binaries actually get executed. So I know in a lot of your class you've been, in your previous maybe classes, you've looked at MIPS binaries or those kind of things, but we're actually looking at real x86 binaries because as we'll see here, we need to be able to when we get to the memory corruption style vulnerabilities, you really need to understand what's going on to be able to exploit those. So what we're going to talk about now is different types of attacks. So this is a slide that I kind of take in my grad class. So to kind of 545 to give everyone kind of how we or what kind of stuff we talk about at that level. This is kind of a very broad range of different types of vulnerabilities that we cover. And so we're going to, in this class, this is an undergrad class, we're going to touch on what I think are kind of three of the most interesting and cool types of vulnerabilities and how to exploit them. And so we'll dig in here, we'll go over that. This will help with assignment 6, and it should be good. Any questions? All right. Cool. Okay, so we'll first look at file access attacks. So as we talked about, really it's the what I have to do some kind of interaction. I can't just talk all the time. So what are some ways that we can take over and trick an application to do something that it's not supposed to do?
To be someone else.
Can you say it louder? Sorry.
Trying to be someone else.
else.
Beat someone up, yeah, without doing that.
Okay. He said trying to be someone else.
Trying to be someone else. Not beat someone up. Yeah, that makes more sense. Okay, good. Although from this class, I would expect either answer, really. So yeah, okay. So trying to impersonate, trying to break, and that's essentially breaking the authentication of the system, right? Trying to trick the system into thinking that you're somebody else. What else? Yeah, in the back.
Manipulate the stack.
Manipulate the stack. So by basically, and really what that boils down to is by injecting data into the system, if we can corrupt and change the memory or the code or whatever of the system, then we can maybe take over the system and make it do something it's not supposed to do. We'll kind of get into specifically what that means and how we can do that, but that definitely is. So the way to think about that is user input, right? So it's really important to think about like a binary or any kind of application as what are all the different ways that as an attacker I can get input into this application. Because if I can get input into this application, then I can maybe use that input to trick it to do something it's not supposed to do. So what are all the different ways that we input into a application? Like as attackers, what are our capabilities?
Arguments.
Arguments?
Arg-
Yeah, so the command line arguments. So argv, right? So we talked about earlier that when we run programs, right, we call we even when we're running it in the command line, right, we type ls. What does the shell do? The shell looks up, tries to figure out using the path variable what ls are we talking about, and then calls execve on bin ls, passing in any arguments to execve of what we have in there. So this is kind of so fundamentally, when we execute another program, we control the argv. We control all the arguments that get passed into this function. Yeah, that's great. What else?
Standard in.
Standard input. Yeah, that's a great one, right? So it's kind of the one we're most familiar with, right? We're running an application, we give it input, it does something, processes that input. You've done this yourselves in the secure house examples. So in homework 2, when you had to give input to an application, so other people's secure houses application to get it to crash, right? That's an instance of attacker controlled input causing an availability problem on an application. Great. What else?
Like F opening the file.
Files, right? So why do attackers control files? Or when can attackers control files? Is it all the time, every single file?
I'm sorry, I didn't hear that. Okay, if you make the file controllable, is that what you said?
If you make the file, then you control the file. So as a program, you have to be careful what file you read. If you read a file made by the adversary, it's dangerous.
Yeah, perfect. So yeah, thank you. And shouting is appreciated. So yeah, exactly. So it's about if you can convince an application to read a file that you, an attacker, either created or control, then fundamentally you might be that is another way that you can feed input to this application. So as an attacker, we can maybe control what file is opened. So by altering the path to the file, or we may be able to control what the contents of a file are. So in all of these ways, depending, and again, this is depending on how the application actually works, it can give us the ability to control the application. So that's kind of the important thing and this is why I'm reiterating it from the last lecture, is understanding all the different ways that inputs get into a program is incredibly important. And this exact same mindset will help you on assignment 6 of looking at each of these applications and saying, okay, what's going on here? Like, how does it work? So that's the reconnaissance phase, right, of breaking the bank. And then you need to understand what exactly is going on. Where does my data feed into this program? And maybe how can I use that to subvert its behavior? Cool. All right. So okay, cool. So, and somebody mentioned fopen, right? So we know that we as a program, technically we can't mess with files ourselves. Who can actually open and read and write to files? The operating system, right? So through system calls. So that's what was just mentioned. Let's see if I can bring up my terminal and see if this works. Everybody see the terminal, even in the back? Yeah, thumbs up in the back. Thank you. Oh, I think it's open, right? We had to open. Okay. So we look at the open function, right? So this is the open syscall. Here we're calling open, we're passing it a path name and flags. So you've all written applications. Have you written applications that open files before? A C or C++ application?
Yes.
Yeah? How do you do that?
Use the F-string library.
Use what?
F-string library.
The F-string library to do what?
Well, the F-string
Yeah,
library.
he's asking to do what?
Oh, to do
Oh,
what?
to open I mean, how do you open a file? So literally you're coding a C or C++ application.
A path string?
Yeah, so you give it a path, right? Like a string. So oftentimes as an application, we maybe hard code the string right? So we may say open a specific file based on a string that we already know. And so that would look, let's see, I guess we can pull up Emacs. We don't do a lot of demos. Okay, is this big enough? Can you read that in the back? More or
Yeah.
less? Yeah?
Yep.
Okay, cool. So we want to call open, right? So we want to open up a file. What file do we want to open? Somebody give me a file.
File.
Man, that was lame. How about
ASDF. Shadow.
How about home root grades? How about that? Yeah, grades. Everyone likes grades. All right, then I don't remember. Okay, here's the flags. So we want to open it up for whatever.
Read write.
Read write. Yeah, there we go. Boom. All right. So this will give us a file descriptor back.
Can you make the font larger? Font. Okay.
Can I do what?
The font.
Larger?
Yeah.
Yeah, that's tricky. I don't remember how to do this on Emacs. Is Max there? He would know.
I don't use it.
Does anybody else remember how to make the font bigger? I had a function, but... there we go. Wait. I had it. There we go. The solution is obviously execute some Lisp code, and you change this to like 22. How was that? Better?
Okay. Yeah.
Okay. Cool. So we have this line of code here, right? That this is a natural line of code. So, okay, let's go through some examples. So when we call this open call here, and we're passing in this path argument, right? Do we know exactly what file is going to be opened?
Yeah.
Yes. Why? What is that file?
Well, because the path string specifies how to get to the file. That's a specific file on grades.
Right, because it's an absolute path, right? So we have /home, /root, /grades, right? So either that file and those directories exist or they don't, whatever, but we'll access that same file. How is that different than this example? Oops.
One's relative and one is absolute.
One is relative and one is absolute. So what does that mean? Can you explain?
So relative would be, like, say you're in a directory home, it's going to be any of the files that are, like, maybe directly in that folder or whatever the path you have to give it has to be from the from the perspective of home. But the absolute is from the perspective of root. If we're using like a Linux system, it's from C / if we're using a Windows system.
Right, perfect. So yeah, so the important thing is it's all in reference to your current working directory. So every process has a different current working directory. Normally when you execute a program, your current working directory is whatever that program executes. And so when you open something like this, like grades, right? So that's going to look in the current directory to see if there's a file called grades. If it is, it opens it up. And this is essentially, you can think of, and that's the point of a relative file. It's specified based on where the process is currently executing. What's the directory of the current process? Whereas this is always going to get this same file, right? So as attackers, when we're attacking a setuid binary, who controls what directory the program executes in?
Attacker?
Yeah, the attacker. Perfect. Yeah, I wanted you to just yell it louder. Really get into the spirit of things, right? So the attacker. So just like we can control the arguments that get passed into a program when it executes, so we can control argv. Similarly, we can control what file, what directory a program executes in, so that we can control this parameter here. We can control where it looks for files. Perfect. Second thing. So what if, let's say I'm writing a program here, and what's it? Grade student, and I'm passing in a name parameter. You can all see this, right? So now, rather than having my grades all in one file, because I'm very smart, I'm going to have each of you have your individual grades based on your name, right? So how would I write that based on, let's say there's like either a subdirectory or a file inside grades that's your name. How would I open that proper file?
You can concatenate the string to name.
String concatenation, right? Exactly. Perfect. So this is all something. So my C is slightly rusty. Let's say, you know what? We'll do string concat. String concat is good. So we can do home root grades, and then slash, and then name. Path. So that, is that right, actually? Somebody? So this is why we always like our man pages, because we can look here and say, okay, yes, concatenate appends the string to the destination string, overwriting the returning byte. Oh, that's bad because it's buffer buffer overruns are a favorite avenue for attacking secure programs. That's true. What's the string cat that actually gives me a new string from it? Anybody know?
Isn't it just string CPY? Isn't
String
that-
CPY? Yeah.
Yeah.
I think you're right.
Just allocate new memory in the string.
Yeah, all right. So this is why it's hard to code correctly in C. Let's do character pointer path equals malloc. All right, we want to do this correctly. We will do character pointer dir is equal to this. So we want a pointer that's the string length of name plus the string length of the directory. And then we need a +1 for what? The null byte. Yes, perfect. So now we have enough space for the path. So then we, so now we can first string cat the directory onto the path. And then we can string cat the name onto the path. So now we should have a string that is the directory concatenated with the name that has enough bytes for everything. And now we need to open the path. Should we verify that we're correct? No? You're all happy that this code works? Everyone's 100% clear? Yeah. All right. Okay, so is this, first thing to ask yourself, is this like natural code? So another way to do this would be string or s printf, so string printf. But is this something that people do normally in programs?
Yeah.
Why?
Because we never know how big the user, or like what the user will input.
Because we don't, sorry, can you say that louder?
We never know what the user will give the input as.
Right, because oftentimes our programs will do things based on user input, right? So even something like, let's say, a SQL server will have, depending on what table, which is basically user input, somebody wants to access, or what database, those may be different files, right? So it may need to read a different database from a different file depending on user input. What are other examples where you're choosing a file based on user input?
A save game?
A save game? Yeah, so for games, like a saved game state, yeah, it's getting input from the user in order to open up that game file. What else?
Word processor.
Word processor? Yeah, fundamentally, right? This is actually something that's really fundamental to everything you do. You're opening up files based on user input, right? So looking at this code here, we think about what is the developer's intention at this open statement. So what files did we want this program to open?
Great.
grades.
or you know,
Grade files, but specifically where?
put that back.
In that path.
Right, in that path. So as a subdirectory. So the developer, you can see the intentions here, right? The developer only wants to open files that are in /home/root/games. Or grades, sorry. I don't know. Oh, somebody said games. That's right. Home root grades, and then only files from within there based on the person's name. Right? So what's the problem here? Is that constraint true? No? Why not? So what you're an attacker of this whole thing. So this is another important thing to think about. So this function here, you're an attacker. What do you control? Do you control this directory variable?
No,
No, why not?
because it's static.
Yeah, it's hard-coded, right? It's hard-coded as this string. You cannot fundamentally change this variable. So what things do you control?
Control path.
You control path, but how? Do you control path at this point here?
It's from the name.
It's from the name.
From the name? Yeah, so from name, right? So you as an attacker, you control the name, which is the input to this program. And then what does the program do with that name? Concatenates it to the path, to dir, essentially, right? So it first concats dir in there, and then it concats name, and then it calls open on it. So as an attacker, by controlling name, can we violate the developer's assumption that we are only opening files that are inside of /home/root/grades? How?
Names start with ////.
The name that starts with ////.
Yeah, what do you want to ..
You're going to compare to it.
Yeah, but what do you want to input? You're an attacker.
Just do that like 3 times and then go to etc shadow.
etc shadow.
Yeah, like that.
Okay, so if name, the attacker inputs name is this string. So let's kind of walk through this just through like pseudo. Can you all see this comment? I know it's a little weird. The colors. Not so great, but anyways, so if we walk through this code, we know directory is this value. We know path is going to be the string length, enough bytes that is the string length of name plus the string length of directory plus 1. So after here, path is essentially equal to the null string. Then after this string concat, path is going to be equal to this, home root grades. And then we're going to concatenate our name onto there. So path will be home root grades, and then what? What happens to these dots? Do they get mixed with anything? Do they get... What happens here?
It's appended.
Yeah, just appended, right? So have we broken? I mean, is this allowed by the code that we're looking at here? Yeah, is anything preventing us from adding these dots in here? No, it's fundamentally just a string, right? This is just a string. What is a string? A sequence of bytes followed by a null byte, a 0, right? And so we didn't violate that at all. And then when we pass this path parameter to open, what does the operating system do?
It opens up file.
It's going to open up what file?
Opens that file.
Cat file.
Yeah, so it's going to open this path, and it's going to resolve this into the actual file. So it goes, okay, home, root, grades, okay, up one, etc shadow, great, here's the etc shadow file. Did the developer ever intend for a user to be able to open etc shadow?
No.
No. But as an attacker, we're able to violate those developers' assumptions and make the program open whatever file we want. This is the root cause of a key aspect of a lot of file attack access vulnerabilities. So, sorry, I need to make you small so you can see this in the recording.
Why it's so common for usernames to not be allowed to have like slashes?
Is that the reason why the usernames are not allowed to have slashes?
You mean the usernames for our system, like the Homework 6?
For any system in
For any
general,
system.
like
Ah.
lots of like that restriction.
I can't say that is the only reason. You could theoretically have that, but yes, when you have, especially on most systems, your username maps to a home directory that is a directory. I think they very conservatively make usernames. But yes, this is where you can get into. Actually, this every year somebody manages to create a username that's weird and Unix doesn't like and breaks my scripts. So when I was creating the Homework 6 server, I had some stuff in there to replace certain characters with underscores, and somebody found a new one. Actually, I think it was a slash. So somebody had a slash in their username, and that broke stuff. So I had to change their username slash to underscore, and then everything worked. So yeah, so this is kind of colloquially known as essentially the ... attack. And the reason why we're talking about this here is we just talked about there's a lot of other applications that actually build up and open files based on user input, right? It's not just the C programs that we looked at, it's all kinds of programs. Websites actually do this a lot. If they're storing, let's say, image data, so have you ever uploaded a picture to a website?
Yes.
Yeah, it has to store that somewhere. What if it used your name to decide where to store it? You could potentially overwrite different files of the web application server. So this comes up in a lot of different contexts. So, oh yeah, this is why did string end count? Anyways, whatever. Okay, so yeah, here's another example, which we basically already did. So by inputting as many ... as we need to, we can basically escape the directory that the developer wanted us to be in and access any file in the file system. The other name for this type of vulnerability is the directory traversal attack. Why? Because we can change and move to arbitrary directories at will. Cool. Questions on this? No? So how do we defend against this?
Prevent certain characters from being inputted.
So like here? So how do we how would we change this code to make it safe?
Regex.
Just an if else statement. Just say if as
So,
flashes.
and if condition to check if the string has any slashes or anything. Just comparing the strings.
I think it's like string toke, or actually I can't remember how you check, but yeah, you could write in pseudocode, you could say, well, if I was writing Python, you'd say if, well, there's two ways. Okay, so let's think about this. So what do we say? Dot, slash, what other characters don't we like?
/1.
$sign.
Dollar sign. Why don't we like dollar signs?
Environment variables injecting into your code.
Environment variables injecting into your code.
Yeah, we're talking about paths right now, so let's ignore that. But so let's just say right now we just want dots and slashes. In name, return null or something, right? So this is not valid C code, but essentially you get the idea. If there's a dot or any slash in name, then return it. So essentially what we're doing here is blacklisting what we think are dangerous characters for name. So we know that name is used in open, and so we're saying let's block any dots or slashes in name. So is this safe?
Safer.
Safer, sure. Yeah, you know, being safer is always better. Is it, I don't know, so is it the best solution? What's another way we could do it? So this is where essentially blacklisting characters that we know to be bad.
You specify what is allowed, or just alpha?
Yeah, so essentially we can whitelist it and specify what characters are good. So we could say something like if, so we could look for, if I was writing a regular expression, you could say A through Z, 0 through 9. So alphanumeric, lowercase a's, uppercase a's, 0 through 9. So I could check it with the regular expression, or check every single character and say you could do it in C, write a loop to check if every character of that string is alphanumeric, and if it's not, return. So what's the fundamental difference between those two approaches?
There is actually something wrong with the screen right now.
Oh, there's something wrong with the screen?
Uh,
Well, you can't see this nice regular expression I wrote?
it's good. It's good.
Okay.
One's inclusive,
One
one's
is
exclusive.
52 something characters. I don't have to check every 250 character types. Minus 2.
Okay. So differences in, let's say, maybe the checking code in this case, but blacklist, blacklist could be just as, I mean, depending on what the specific attack we're trying to prevent is, blacklist could be even more restrictive or even have more characters to check. So I wouldn't call that necessarily a fundamental difference.
A white list is nicer because we know what we want. We may forget things we don't.
Right, so it's easier, in some sense, so they both can have problems, right? It's easier for a whitelist to be correct because you can be very conservative, right? Like, can you have dashes in file names?
Yeah.
Yeah, you can. Am I allowing that here?
No.
No, I'm not. I'm being very conservative in what I'm accepting as valid input, right? So the other thing, and then with blacklist, so what we blacklisted before were the characters dot and slash, right? Are those are those dangerous characters when used in an open path for every single possible file system?
Probably not.
Yeah, the short answer is I actually don't know. If you're writing, I think on Windows, you can actually represent paths with slash. So you can say something like open, I think this used to be the case. It may be like slash foo slash bar slash something. And it will open that. So the operating system has different behavior here. So this is again, a problem with, actually could be a problem with both black and white lists, but blacklisting characters, the blacklist has to be complete. If it doesn't have every single possible character, then you can have problems. Questions? Cool. All right. And now we will go to, let's see. Sorry, I'm just clicking on random stuff. Okay. We are going to go to, okay, cool. So path and home. So let's go, and we may have already done this before, but if we have, it should be pretty easy. Everybody see the screen?
Yeah.
All right, cool. So, okay. Okay, so when I type in ls, how does the shell know what program to execute?
It searches the binary and searches your path.
Yeah, so it needs to, right, so how do I know, what's the command I can run to tell me what is the exact binary that's going to be run by ls?
Which?
Yeah, we have which, right? Which tells us exactly what program will be executed, so we can do which ls. It tells us /bin ls. So when I do /bin ls, that's how I can execute it directly there. Great. And now it's important, again, as we mentioned, and this is what it all comes down to, documentation and understanding what's going on. The execve syscall has the first parameter as a file name, and this must be a absolute path to a file name. So you pass in a file name, argv, and an environment pointer. So where does it say that? file name. Okay. So, anyways. So, we need some way to be able to specify, hey, when I type, I don't want to have to type in /bin ls every time. I want to be able to type ls, and I want the shell to figure out what ls I'm talking about. And this is done by using an environment variable called path. So the path environment variable specifies a colon-separated list of directories to search in for a binary. So when I type in ls, the very first thing that happens is my shell goes in and it looks at, okay, is there an ls in /user local sbin? Is there an ls in user local bin? Is there an ls in user sbin, and then user bin, and then sbin, and then finally bin, and that's where it finds it, so it stops and uses that one. So this is a kind of early circuit termination. As soon as it finds one, it stops and it executes that one. Great. Okay. How does that help us? Well, so, okay. So here I have, void. Let's say I already know the file. That doesn't really matter. Cool. Okay, so we're here. We're writing some code. We're continuing our amazing C grading program. And we want to write a function that shows the person who runs it the current grade. So we'll keep it simple. Okay, right now we just have one grade file. So we have our grade file. Now, I can, as a developer, so at this point, and I have the highest confidence in all of you, you can write a program that reads this file and outputs it, right? So how would you roughly go about doing that? Open the file, then what?
Right mode.
Sorry,
Right
what was
mode.
it? Write mode, so open in write mode, or read mode, and then what?
Parse it and hand it to Rick.
Pass it and then print.
Yeah, so read in, you can call the read function to read in byte by byte of the file, and use write to write out byte by byte to the file, the standard out, and you can do that. But this is a Unix system. One of the core principles and idea here is that you shouldn't reinvent the wheel if you don't have to. Is there any other utility on, like any other program on a Unix system that you can reuse that will show you the contents of a file? Yeah, cat, right? So the cat command, if I were to go and undo cat, I don't know what you want me to cat. Oops. Cat test. So I can see the contents of files. I'll do it again just so it's up more towards the top. Right? I give it a file name. I call cat. I give it a file name, and then it tells me, hello, class. So it turns out there's a great function in libc called system that executes a shell command. So let's go and try that. So so now we could do open file, read file, write to standard out. Here we're talking about at least 1, 2, 3, 4, 5 lines of code plus a loop that we have to do. We have to make sure we do this correctly. Or we can replace all of this by so which approach would you choose?
That's the one I'm doing it for.
What?
It depends on what you're doing it for.
Why does that depend?
Because am I trying to be more secure, or am I trying to be efficient with the code I'm running, or am I trying to be efficient with the amount of code I write, or like there's 100 questions that go into any design process.
Trying to be efficient.
True. I think there's a interesting sort of Occam's razor in effect. If you can have two pieces of code that do the same thing and are the same in terms of security, you should choose the simpler one that has less code. There'll be likely to be less bugs. More lines of code is more maintainable, is less maintainable. So the less code you have, the less things you have to maintain. So if I can replace 10 lines with one line of code that does functionally the same thing, you'd have to worry about, am I running this on systems that have cat or don't have cat, or that have a weird version of cat? So that can definitely could cause problems, and it'd be something to think about. But if I know I'm going to be running this on a Unix-like system, I can be fairly confident that they'll have cat and that this will do exactly what I want it to do without me worrying about it.
Yeah, but that's more vulnerable to attack.
Well, sure, that's why we're building this up right now. I will say you can do this securely. There's a way to do this securely.
Oh, okay. Fair enough.
Cool. Okay. But let's dig in here and get under the hood. And again, remember, this all comes down to what's actually going on. So here we call this system call, which calls into libc to actually do this. But what does it do? So let's look. Man system. Yeah, can you hear me? It says my connection's unstable. Can you hear me now?
Yeah, that's fine.
Okay. Yeah, it said my connection was unstable. All right. So I didn't say anything important. Okay. Let's read this nice documentation. It says, so system, pass it a character pointer, a string. The system library function uses fork to create a child process that executes the shell command specified in command using exec-l, important that it's not exec-ve, but we'll look at this in a sec, as follows. So it calls exactly /bin/sh, then passes in as argv0 sh, then passes in as the other argv1-c command, and then our command. So system returns after the command has been completed. So, and when I'm here, so what if I did bins, so what was it, bin sh-c ls? What do you think this is going to do?
Execute ls in a separate shell.
Yeah, create a separate shell and execute ls. So going back to my example, if I pass in cat test, this is going to execute cat test, right? So how does sh know what cat to execute?
Wow.
What was that?
The path.
The path, just like when I'm here sitting in front of my terminal and I write cat test, right? This is the important thing to realize and understand is system is a function that is basically saying exactly as if you were at the shell command, typing in cat space /roots /home root grade. That's exactly what's going to happen. So cat test. Okay, so now, if this program is a setuid program that's running, who controls the environment variables of a program that runs?
The attacker.
The attacker, right? As an attacker, we control that. We control path. So what does that mean for here? So actually, wait, before we get there, again, another thing to reiterate, what did the developer intend to do? So we were the developer here writing this line of code. What do we want to have happen?
Output the greatest standard out.
Yes, to execute the program cat, bin cat, and to output /home root grade. But can an attacker violate those assumptions?
Yeah.
How?
You could change the path for cat to point to a different program.
Yeah, so you want to try it out? Let's go. All right, so this will be very simple. I need standard lib.h. Int main Okay, so here we go. I'm going to say system, and I don't have this file, so let's just call it system test for right now. Right, so test was that file that we just had in that directory. Everyone agree with this code basically is roughly the same as whatever we had?
Text is kind of hard to read.
Oh, sorry.
Because of the call.
How about now? Is it worse?
That's better.
That's better.
That actually was better? Okay, cool. High contrast. Okay. So everyone agree this code roughly does what we were talking about before? Yeah. All right, let's compile it to see any mistakes I made. Okay, cool. So we just ran that. We can see that it's calling hello class. We can actually use various, we can use various programs in order to understand more about what's going on. So strace is going to execute a process and tell us all of the system calls that this process is going to make. Now, there will be a lot of output here. Do not be freaked out, because we're going to try to find the important one that we were looking for of strace, of that, the right to call cat. So if we look up, we have an exec VE. So this is actually, we can see us, this exec VE ./a.out. This is us executing it. Stuff happens to set up the loader and all kinds of other stuff. Where is... Oh, I bet the fork. Okay, this does not show what I wanted to show. That is... All right, well, we'll ignore that for now. Maybe I can figure out what exactly I want. Fork. Yeah, okay. I want -F, I think, to follow the fork, because we're going to fork a child. So let's see if that works. Well, here's the read and the write of hello class. Okay. Open test. Where's the exec VE, though? Ah, all right. This happens sometimes with live demos. Okay. I feel like it's got to be close. There we go. Found it. Woo! Success. Okay, can you see that line?
Yes.
Cool. So this is exactly what happens when we called that system call, right? This is straight from the documentation. It's going to call exec VE /bin sh. The argument 0 is sh, argument 1 is -c, and argument 2 is cat test. Okay, perfect. And then bin sh is then going to look up and figure out where cat is. So, simple binary, right? We looked at this code, simple binary. How do I trick it to execute a version of cat that I want it to execute?
Change your path.
Change the path to what?
Have your cat before the real cat.
Hello cat before the real cat.
Okay, so let's say I had my path just be /. So this is one way that you can run a program to just change the environment while you run it. So this is basically saying, well, let's try to set path to nothing. I wonder what that will do. Yeah, okay, perfect. So why did it say cat not found? Right, because there is no A folder here. It has no idea where to find this, and so it can't find cat. Okay, so we need a cat. What do we want our cat to do? Maybe just say, you were hacked. Yeah? that good?
So I
You
don't
can't
think
see it?
anybody can. No, no.
How about now? So there's a simple shell script that says you were hacked. So we know that if this executes, then we were able to trick that program into executing a program of our choosing and not their choosing. All right. I need to make it executable. So okay, I can execute that version of cat. It says you were hacked. Great. So now I run a.out. It still says hello class. So what am I doing wrong?
You're not setting the path.
I'm not setting the path. So what does the path need to? So I can set. Oh no. Okay, so path A. Okay, that didn't work. What about cat? Why isn't this working? How do I fix this?
You need to put a directory.
I need a directory. What directory do I want to use?
Your current one?
Which echo?
Dot, the current one?
Yeah.
Yeah.
Boom. There we go. You were hacked. Right? So why did this happen?
Change the path variable to tell it basically to reference the current directory from that.
Yeah, so we changed the path to set it to be the current directory. And so binsh, when it executes, and when it's trying to execute a cat system, it says, okay, well, what cat program does this person want me to execute? Or does this program want me to execute? And then it looks, it says, okay, I'm going to look in the path. Well, the path is dot. I'm going to look in the current directory. Is there a cat? Yes. I'm going to call /cat test. And that's how that gets executed. So we're just able to completely change the executable. So if a.out was a setuid binary, then what permissions would cat be executed with?
Root.
Yeah, root or whatever. If it's setuid, whatever the elevated permissions are from that setuid binary. Perfect.
So how come changing the path variable didn't change it on your entire system? Like, cat still work?
Yes. So there's two ways to change the path variables. You can do, let's say, foobar :path. So now I've changed the path using export. I've changed the path for all other commands that I'm going to execute here. So I've changed this environment variable. If I say path equals dot, and I say, what, env? Oh, yeah, okay. That's actually good. So env prints out the current environment. So if I look in here, yeah, I can see that path. So this style is you're able to execute one command by changing just this environment variable for that one command. So it doesn't affect your path once this command is finished executing. Does that answer your question?
Yeah, thank you.
Yep. Cool. Okay, path there. Great. And there's other, so it's not just system, there are other functions. execlp and execvp also use the path variable to locate applications. So it's important to look at and to understand what program is this trying to execute, how is it trying to find that command, and that way, can you alter the path variable in order to change what program is executed? Similarly, in a similar vein to the path environment variable, and I'll do this real quick. So when I do cd tilde, how does the shell know where tilde? What is tilde? Home. It should be the environment variable, and it's specifically the environment variable home. But if I set home equals root, and I do cd there, that didn't work. Yeah, there we go. Okay, cool. So by changing the home environment variable, when I do cd, so now again, this is another instance where I have what looks to be something fixed, right? I have a tilde, which specifies the home directory, but by altering this environment variable, I can change what that home directory is. So similarly, if an application uses a home relative path by using a tilde, then an attacker can modify home variables to control execution. So everybody understand these two vulnerabilities? Or have questions about this? So how do we fix these? So you're my expert security engineers.
Somewhere where it can't be accessed by outside systems.
So how do I change this code so that it's no longer vulnerable to somebody messing with the path?
Rather than saying cat, just write the actual path to the cat you want.
The full path to the cat I want, which has been cat. So if I do this, now I'm telling the shell, because remember, system calls bin sh. And we know the shell, if we specify the exact program to execute with an absolute path, it has nothing to do. It doesn't need to do anything else here. So if I do this, compile it down, a.out, hello class, and we'll go back to my vulnerable one. Oh, no, not that. Right, so here we now executed our vulnerable execution by changing the path, but we're still not able to change what program gets executed. Cool?
There's a question.
Yep.
If you wrote like at the beginning of your program, like the first line, system, and then path equals, would that overwrite anything that the user would put as their path?
Yeah, okay, so the question is, if you change the path, so I don't, let's see. Actually, I think this would work. I'm fairly certain this will work. So here we're hard coding a path. If we tried to do it up here,
They cannot see it.
oh, sorry. Let me finish writing this. And nobody likes my color choices, do they? Okay. So we have two instances here, right? So this first one, this export path equals /bin. This is not going to take effect for the other system calls because this is the system call forks another process, so the changes to the environment don't propagate. I believe with this second one, this actually would fix it because we're specifying, hey, for this command, use /bin. But of course, here it's kind of silly. We know exactly the command we want to execute, /bin cat. We can use, to further answer your question, we can use put env. We can use the command put env to change the path environment variable for our program. So in that case, yes, we can specify. So we have two ways of doing this. We can test this really quick. What was the, standard lib.h. So if we go, same thing? Okay, good. So what we can do is we can do put env. So this changes our program's environment to have a new path of our choosing. And then if we do bin cat, so let's go and hopefully you can see this here. So by calling put environment, we're changing the environment for our program, and then that way we've controlled it and hard-coded it for the rest. So if we try this, yes. So we've been able to fix it here because we're specifying exactly the path. And we're essentially not using the attacker-controlled path. Yeah, good question. Other questions?
Nope.
Cool. All right, so digging deeper into system, so not only do applications invoke external commands to carry out specific tasks, right, as we saw, so using cat to cat out a specific file, what if we essentially combined the two things that we were looking at? So what if we were combined, so what if we had a calling system, even with something like bin cat hard-coded, but then the file parameter we as an attacker controlled? So for instance, and as we saw, system executes by calling bin sh-c and then whatever string you pass to it. popen is another one that does this similarly. And so let's look at a simple example. So here's some C code. We have a buffer here. We're going to cat/var log and then %s, where %s is argv1, right? And so we're going to concatenate and we're going to put argv1 wherever this %s is. So what's the intention of this line? So what does the developer want to have happen here?
Cat a
We
specific
printed out
file.
some log file.
Yeah, so to cat a log file that's given from argv1, right? So this could be a program to output log files. And it's specifically only supposed to output log files that are in var log. So we'd actually know as an attacker, well, one thing we can do is we can use a directory traversal to cat out any file, right? So how would we do that? What would we put in for argv1 to trigger a directory traversal? Yeah, .. etc shadow, whatever other file we want. We can get it to output any file we want. But we want to do more. We want to be able to actually execute commands as the root user, not just read files. We want to be able to do arbitrary things. So how can we trick binsh into executing different commands?
Semicolon,
A semicolon? Why is a semicolon important?
because it ends the previous command and starts another. Do you want to?
Yeah, so if we could do something like foo semicolon cat etc shadow. And okay, let's look at this. Grab this. Okay, here's that same code. So what kind of command do we want to execute? Let's say we want to delete a file. Do we like deleting files?
Yes.
Yeah.
Sure, right? We can mess with the system, mess with availability. So if we input, so what do we input for argv0 to delete a file? Or argv1, sorry.
Semicolon space rn and then like the wildcard.
Semicolon space on, and then yeah.
Wow, that's pretty vicious. Okay. Cool. So after this snprintf command, right, it's important to, okay, so what is command going to be here based on this string concatenation? So command is going to be cat space /var /log / and then semicolon space rm star. Everyone agree? That is the result of this snprintf based on this argv1. Yes? Guys, you nodding? Perfect. Okay. Then when we call system, why does system end up thinking that we're trying to execute two commands?
Semicolon.
What was that? Louder?
The semicolon.
The semicolon. Why specifically? Why does it even care about this semicolon?
Because you can execute two commands on one line if you just separate them with a semicolon.
Yeah, and we know that system ends up calling bin.sh, which is a shell. So it interprets whatever commands we give it as if we're on the shell. So all the cool, awesome commands that we can use on the shell, like semicolons to execute multiple commands work, or backticks to execute commands, or $ parentheses. Anything we can do as if we were sitting on a terminal using a terminal, that's what we can use here. So here, bin.sh gets this string and says, oh, you want to do cat/var/log /rm star. Great. I know that those are separated by semicolons. This is two different commands. One is cat. Let me find the program for cat, execute that, and then execute rm star. And then it will start deleting all the files in the current directory. I will not run this because that would be bad. Hello? Okay, cool. And so this is fundamentally gives an attacker more capabilities than they would have just by reading files. So what are some other things we can do? We can read files, we can delete files. What else?
Run other
Are you guys
programs.
talking? Because the sound is super weird.
Run other programs. Run other programs.
Oh, wait, just a second. Maybe it's me? Hello?
Hello.
All right, I can see the wave. I cannot hear you. Maybe you'll see this on the video and hear it. It sounds like you're talking from the bottom of an ocean. I don't know exactly what's happening. Okay, so I'm going to finish up with an example. Okay, what I was just going to ask you what I just said, but I suppose that's on me now.
Hello.
So, okay. So finishing up here. So, yeah, okay. So we can read files, delete files. We can also execute arbitrary commands. We can do really cool stuff. We can have what's called the reverse shell. So we can have, and you can look this up. You can find examples of reverse shells online where a program can talk to you. It will basically a reverse shell will connect to you on a given IP address and port, and you can type commands as if you were on the system. Essentially, we could do anything we want. We could drop our SSH key as the user so we can access their system. We can drop PHP files into their web server to execute PHP code. We could access their database. Literally, we now have full code execution as that user. So we can do all kinds of super cool stuff. Change their password to what we want. I think we can do that. No, maybe you have to know their password. But anyways, fundamentally, we can do all kinds of cool stuff. So I want to show you one super cool example of this. I'll get you done in time. So there was an example in 2014. There was a bug discovered in how Bash processes an environment variable. And essentially the idea was Bash program can pass through environment variables, not just data and code, but also it can pass function definitions. And it turned out that if you set an environment variable with values started with parentheses followed by a function definition, Bash would essentially interpret that and evaluate it as code. And it was executed by Bash. So this seems like a weird behavior, but fine. I don't know what's really the security implication here. So it turns out that you can execute arbitrary codes by appending commands to the function definition. And so, for instance, if you had a limited access SSH account, so anybody use Git over SSH? Yeah, so Git is literally giving you SSH access to their system, and they're setting it up such that your SSH access is limited to only be able to essentially talk to Git. But as part of SSHing in, you can set environment variables. So environment variables are set based on the user for that command. So what you could do is you could SSH to their system, set an environment variable that would execute Bash code on their system as that user. So you could pop any kind of these restricted shell SSH accounts. So this was the command. The original command got put into an environment variable. You could cat edz shadow. You could kind of do whatever you wanted in here. The other area where this was highly vulnerable is web applications. So specifically CGI-based web applications, which there were still a lot of at the time, basically pass HTTP arguments from the user to the application through HTTP, and you could execute arbitrary code on a web application simply with one web request. So it's actually, the shell shock, I think, was one of the first instances of like a vulnerability with a name and logo and website and all this stuff. So you can go look this up. The other super interesting thing is that this bug was present in Bash for 20 years and nobody figured it out. It took literally 20 years for somebody to realize, oh, wait, there's this weird functionality that nobody uses that actually lets you get arbitrary code execution. So there are insane bugs still out there that are command injection style vulnerabilities. The other thing I want to say before I let you go is that these type of command injection vulnerabilities, these are incredibly important. They still occur on almost all types of applications. So we're looking right now at binaries, but they still exist on web applications, PHP applications, Ruby on Rails. Basically every type of environment where you can shell out and execute commands on the shell is potentially vulnerable to these types of vulnerabilities. So it's super important to look at that. All right, I got 4 minutes left. Go cool. You probably have to, if there's any questions, you'll have to chat them because I can't hear anything you guys are saying.
Any questions? I'm sorry?
When are we getting our test grade fast grades?
The test scripts? Test grades?
Oh, it's really weird.
Probably by next week. I think by next Tuesday. Yes. I'm sorry? Same question? Yeah.
Okay, I assume everything's going good. I will see you all on Tuesday.